Well, it looks like we can start. Welcome back. For the others that aren't here with us today, I'll consider them here in spirit for when they watch the video later. But for the things we've got going on today, we're kind of in an exciting spot for the course. Week number 7 marks the 75% mark for the entire semester. And really, as far as the content goes, we're just about wrapping up right around week number 7. We're first going to get across to exam number 3 on Monday as our typical day for the exams. And if you haven't scheduled your exam 3, just see the instructions in Canvas like before and get it scheduled as soon as possible. And as far as the content goes, I believe this exam came up to 9 questions. If you're caught up on the homework from sections 3.8 to 4.7, you can study further by taking a look into the feedback I gave on your homework on any problems you might have missed. You can look into the further problems on the sample exam 3 problems here as well. And if you feel like there's any section that maybe was a little trickier, maybe it could have been, say, for example, section 4.4 on L'Hopital's rule. Another strategy for studying on the exam is go to the very top of the Canvas page under blank lecture notes. If 4.4 seems like a good section to review, then go to that section 4.4 here, either the PDF or the Word document. This is now essentially just a worksheet, and you can solve the problems there to see how on track you are for those problems. You can get the solutions by just going to the Canvas webpage. All the solutions are pretty much posted the moment we finish them, so you can check them as you go. So the problems that we did in class, the problems that you did in the homework, are considered the excellent candidate problems for reviewing on this upcoming exam. And the sample exam 3 problem set are just additional problems. Some of them a tad more challenging, just for the extra practice. Well, aside from the exam, we're going to continue on through section 5.1. And on our Thursday's class, we're going to get into the fundamental theorem of calculus to see how antiderivatives connects with the problem of finding areas and distances, areas under a graph. But any questions or comments at all before we start today? Okay, let's jump back in. So last class, we barely almost finished example 1 in section 5.1. We got this far, which is kind of unfortunate. I hate kind of breaking a problem in half from one day to the next. So let's recap on what we were doing on this problem and then finish it off before taking a look into the next. We're trying to find the estimated distance traveled by a car whose velocity graph in red is provided. It accelerates from rest, 0 miles per hour, to a speed of 120, not miles per hour, 120 kilometers per hour after 30 seconds. We found that we want to use 6 approximating rectangles at right endpoints to estimate the distance. Distance is just rate times time. So any one of these rectangles has a width, that's the time. The distance is the height. This one was about, say, maybe 115 kilometers per hour. So if we multiply those two together, we're really just looking into an area. And so this is how the area problem connects to any kind of problem, say, like this one. We mentioned before, areas are extremely important in the sciences. They could be distances like in this problem. It could represent a force, energy, say, density. It could represent a probability. And the list of applications just goes on and on and on. It's hard to think of all of them on the spot, or a good set of them. So what we did was, for using 6 approximating rectangles, it asked us to use right endpoints. And the summary for that is just R6, 6 approximating rectangles at right endpoints, which we mentioned here as well. The distance is approximately R6. The width of those rectangles are delta t, which is b, the upper bound, 30 seconds, minus a, the lower bound, 0 seconds. Divide by the number of rectangles, 6, and we got delta t to come out to 5 seconds. So with that all in play, the height of these rectangles are for the velocities at a certain time. So the height at v1, the height v at t1 is just going to be the velocity at 5 seconds. And that we would estimate visually at about 50 kilometers per hour. Now we just need to drop in our values, do a quick unit change on this because we need to make this become hours to match the unit, and we'll have an approximated distance. Any questions at all with the recap on this one? Okay, let's do a little bit of dimension analysis on this one. Delta t is 5 seconds, so that means delta t at 5 seconds, we need to get this into hours, so we'll multiply by, we can say 60 seconds to the 1 minute. I was arguing with myself on doing that unit conversion. Units are not my favorite. I try not to make this stuff this kind of work happen on exams, so we can just focus on the calculus. And then for 1 hour, we have 60 minutes. And so this becomes 5 divided by 60 squared. This is a good use of the calculator. So it's that fraction altogether, or we can write it as 1 over 720. So 1 over 720 hours. So in place of delta t, we'll use that unit there. 1 over 720 hours. That's just the width of every one of these rectangles. Since all the widths are equal, we can just leave it factored out there. It distributes through and multiplies all of the velocities, the heights of the rectangles. And so this is just the more compact way to write this. So velocity at time 1 is just velocity at 5 seconds. Let's put 5, 10, 15, 20, 25, and 30 here, just as a reminder where the values are coming from. And their natural unit, the seconds. At 5 seconds, we get a height of, this comes out to 55 kilometers per hour. And then we just add on the next value. Velocity at time 2, we said time 2 is 10 seconds. So that's just the height of that rectangle, 80 kilometers per hour. You don't necessarily have to capture the units if you do a problem like this in homework. But I think it's handy to see how hours are going to cancel. All we're going to get is kilometers. So you really have the right quantity we're expecting in the unit analysis, just kilometers for a distance. And then it's rinse and repeat. At 15 seconds, these get hard to do exactly, but it's understanding you're estimating from a graph. So your answer doesn't have to be perfect. It's within the right ballpark of the expected answer, you'd always get full exact credit. So at 15 seconds, I would guess that that's about maybe 97, 95 kilometers per hour. Let's err on the higher end, 97 kilometers per hour. Then at 20 seconds, we're at maybe 110. Gets harder and harder, it seems, as we go, kilometers per hour. So that one's at 20 seconds. We're now at this one, the penultimate one, 25 seconds. Well, the height here is 120 kilometers per hour. That's pretty high. So maybe plus 117 kilometers per hour. And final term, we knew it reached a speed of 120 kilometers per hour. So we do have that exact value there. Ashton says, wouldn't time one be closer to 50? Well, yeah, I said 55 and time 1. Yeah, I'm not sure where 55 came from, to be honest. If you made a weird estimate like that, it would still be for full credit. But yeah, that looks like perfectly midway between 40 and 60. Let's go with 50 for a better value. So 50 goes there. Thanks for spotting that weird estimate on that one. The final one, 120 kilometers per hour. Barely got that all to squeeze in. Now we have an approximate distance that we can throw in, just pushing this all into the calculator. Any questions or comments to this stage? Okay, As the 1 over 720 hours distributes in, we just have really a time times a rate, which will give us an approximate distance over every one of these different time intervals. And so now in the calculator, this is going to come out as, I guess I didn't need to delete that. Let's carry it in once again as 1 over 720. Doing this on an exam setting is kind of tedious. This is one of the reasons calculators are allowed on exams rather. And this would be a kind of problem that you might see on, say, the final exam. But on a final exam, I don't want to take off credit if you made a simple calculator mistake. So if you have this on paper, everything that's about to go in the calculator, just like this, you showed all the valuations, and I can see the numbers, should still calculate to see if it's reasonable. But if you made a calculator mistake, I know where your numbers come from. I'd probably still give full credit, just knowing that maybe your thumb slipped and you hit a 0 when you meant to hit a 5, something simple like that. So make sure you have this kind of stuff on paper, but let's now throw this all in. 50 plus 80 plus 97 plus 110 plus 117 plus 120 comes out to a distance. Didn't tell us what to round to, just said estimate. So use your best judgment. I would say probably 4 significant digits is good guidance. 0.7972 kilometers. So almost 0.8 kilometers over the 30 seconds is what we would be estimating through the right endpoint rule, R, with 6 subintervals. Well, as we look at this graph closely, though, even though this is not as blunted as an estimation when we just started this problem, every one of these rectangles has area that goes above the red curve. Quite a lot of area to start out. As the curve gets flatter and flatter, the area above the red curve, it gets smaller and smaller. But that still tells us that this is, overall, this is an overestimate. The true distance, the exact distance, is going to be the exact area under this red curve, and it would be less. Maybe not a terrible amount less. So we want to find out ways to improve these kind of estimates. There's different things we could try. We used the right endpoint rule, R6. We could swap that off to the left endpoint rule. That would give us an underestimate, and maybe we could just average those two. That's in fact called the trapezoid rule, studied in Calculus 2. Or maybe we could take a different kind of measurement. Instead of a right endpoint or left endpoint, we could take the point midway to be the height of each rectangle. And there's even more different kinds of ideas to try. One way that this can improve quite a lot is just to increase the number of rectangles. In fact, when we go to define the integral, which is going to be the area under the curve, we want to take a limit as that end right there goes to infinity, which means the widths of all of these rectangles get finer and finer and finer. It starts to look like a saw pattern until it approaches the curve itself. So if we can define that limit just right and find ways to calculate it, we can get the area under that curve exactly. But so far as an estimate problem, that's not too bad, getting that number out. Well, that's our first area estimate problem. In the homework, you're going to be doing problems pretty similar to these. We'll try out a couple more just to get some variety on how these go. Any last questions or comments getting through this one? Okay, well, this one was an application. It felt like the right thing to start off, just an immediate, why do we care about areas kind of problem. The next ones are going to be a little bit more similar to the homework. This is example 2, part A. This one is asking us to find the area under the graph cosine x as we go from 0 to pi over 2 using 4 approximated rectangles at left endpoints. So when it says to use those rectangles, this means we're going to be using the left endpoint rule. And this is abbreviated by saying L for left endpoint rule, 4 approximated rectangles would be L4. So that's how we're going to approximate the area on this one. And let's take a preview on the next one just to tie in more of these kind of notation ideas. The next one, let's unhide it for a moment, says we're going to look at this function. F of x is 1 over 1 plus x squared from -2 to +1. 4 rectangles again. We're keeping the numbers small so that we don't feel like there's too much tedious in this problem. But this time it's saying 4 approximating rectangles at midpoints. Sketch the graph in the rectangles just like in part A. The way we shorthand this is called the midpoint rule. And the nice thing about the midpoint rule is it has a compromise between overestimates and underestimates. So it tends to be less biased compared to the right endpoint rule, the left endpoint rule. Our abbreviation for this one will be M for midpoint. If it said 40 rectangles, we'd put M sub 40, but just 4 on this one again. Again, so that it doesn't feel like so much tedium getting through the problems. So those are our 2 to give a try. On the homework, these instructions are very similar to the ones in the homework as well. It's asked that we sketch the graph by hand and the rectangles. It doesn't have to be pretty, just capture the idea of finding the area. And then we'll determine if the estimate is an overestimate or an underestimate. So all this starts with the curve cosine x. So we'll begin there. Let's sketch that curve as we go from 0 to pi over 2. Cosine is going to be non-negative in that region, so we can just focus on quadrant 1. And maybe before we start putting down the tick marks here, we want to make sure that all of our values we put down correspond to the 4 approximate rectangles for L4. So let's maybe begin by also, as our next step, compute delta x. It was a delta t in the last problem. Delta x uses these values. The formula is always the same, b minus a, divided by n. N is the number of approximating rectangles. So when it says 4, it means n is 4 in this problem. B is the upper end point of the interval, so pi over 2. A is the lower end point, so pi over 2 minus 0. That means this whole thing just becomes pi over 8. So that's going to be our width of all the approximating rectangles. If we list out all the endpoints, just like we did in the last problem, it would look like this. A, we call x sub 0 or x naught, is the left endmost point, 0. Then x1, all we're going to do is add delta x to get all the next points. So it's going to be 0 plus delta x, pi over 8. X2 is going to be 2 pi over 8, or pi over 4 if you prefer. X3 is going to be 3 pi over 8. And X4 is going to be 4 pi over 8, but that's also just pi over 2 if we reduced. Let's write this in as pi over 2 to emphasize that's the upper value, b. So those are all the points. We're using 4 approximating rectangles, but if you count them, that's really 5 points. So here's one important trick to know which points are you using really. If it's left endpoints, it's going to be always these. These here are going to be the left endpoints. And just to compare what we did on the prior problem, when it was right endpoints didn't use the a value, it used the rightmost value b. So right endpoints look like this. We used b, which was t6. We didn't use the far left endpoint at all because t1 was to the right of the interval from 0 to 5, and those points determine the height of all the rectangles. So if it's right endpoints, we exclude the left boundary value, go all the way to the right. If it's like this one, left endpoints, then that would mean we exclude the far right point and use the left endpoint. you should have four numbers when you're using left endpoint, right endpoint, or midpoint rule. And these are the four we would use. So that gets us started. Next thing we'll do is put those points on the graph. First point is 0. Usually we don't label that. That's implied. It's at the origin here. Next point is pi over 8. Then 2 pi over 8, or pi over 4 if you prefer. 3 pi over 8. And then 4 pi over 8, which we reduce to pi over 2. So those are the 4 points that we're going to be using. Now that we know the exact values, we're going to be able to sketch the approximated rectangles in our graph in a lot better of a way. So definitely you wouldn't want to go from, say, like 0, 1, 2, 3, and so on. You want your marks here to match the actual geometry of the problem, the left endpoint rule that you'd be using for this one. So as far as cosine goes, it's at its absolute maximum when the input is 0. Then it starts falling. It falls to an x-intercept at pi over 2. Cosine pi over 2 is at 0. Falls gradually at pi over 4. It's square root 2 over 2, which is about 0.7 rounding, so right around here. And so my rough sketch for cosine, that's not the best cosine sketch in the world, but that's okay. In the homework, you'd be doing this by hand, so it doesn't have to be perfect. So there's the graph. If you want to, you could graph this using technology, screenshot it into your homework if you're doing this in a digital way. But if you're doing this by hand, this would be a just fine way to do it. So we've got cosine down. We have the x-axis to match the problem. Next thing we're going to do is sketch the rectangles that are going to approximate the area under that green curve. Any questions before we begin with the rectangle sketch? Okay, so let's compare to what we did on example 1. On example 1, it was right endpoints. The first right endpoint was 5. So when we went to sketch a rectangle, we went to 5, we went up till we hit the curve, and that determined the height of that particular rectangle because it was the right endpoint rule. However, if we're using the left endpoint rule, our very first left endpoint is at 0. So that means we start right at that value 0. I don't know why that keeps jumping. Let me try to keep it there. That's going to determine the height of the rectangle. So first rectangle goes all the way here. And this is what we mean by left endpoint. We move to the right. We end right at pi over 8 in that interval. And so this is going to be the first approximating rectangle. Then we just do it again. The next right endpoint is at pi over 8. So we go at height pi over 8. It's right here. Move to the right at pi over 4. Those are supposed to be equal widths, but again, it's a by hand sketch, so we use our imagination as appropriate. Imagine they're equal widths. Go to 2 pi over 8. At 2 pi over 8, the height is right about here. Move to the right to the next interval. So there's the height of that curve. Then finally, from 3 pi over 8 to pi over 2, the left endpoint is at height 3 pi over 8. We move to the right, drop a rectangle, and that represents the area with this kind of lazy shading we see here, so we don't lose the curve in green. So if we compute the area of those 4 rectangles, which is fast to do, it's just length times height, we'll have approximated the area under the cosine function from 0 to pi over 2. It's going to ask us if our estimate is an underestimate or an overestimate. You can answer that at the end of the problem, but we can see right away it's going to be an overestimate because every one of these rectangles includes a portion of area above the curve in green. So we'll make sure we say overestimate again on this one. And finally, we put this all together and we're ready to calculate the area. So we can now say area. It's the area under the graph of cosine x. We'll just say area for short. we're using the left endpoint rule, L4. So I'll write here is going to be approximately equal to L4 Then down below, we're essentially just putting down what is the formula for L4 itself. It's going to involve delta x. It'll be delta x times the height of the curve right up here. That's going to be f at x naught, or f at 0 if you write it in that way. I'll write it as f at x naught just to show the formula altogether. So here's f at x naught. And we're going to allow delta x to distribute, so we can write it down a little bit faster. Delta x will also multiply the next height. Delta x is the width, so the next height is f at x1 pi over 8. So plus f at x1. And that's pretty much the whole pattern for getting the area. Just go plus f at x2 plus f at x3. All we now need to do is throw in those values for f at x naught, x1, x2, and finally f at x3. So we've almost got an area. The delta x is pi over 8. Coming from that equation up here when we simplified. When it says f at x naught, we're talking about the curve in green. X naught is 0 on our table for the left, the values we have there. So we're just saying take cosine 0 plus cosine x1 on our table to the left is pi over 8. Or you might be following the graph pi over 8 here, then plus cosine 2 pi over 8, which reduces to pi over 4, plus cosine 3 pi over 8. And then we stop right at that point. So we just need to plug this into a calculator, get a value out. But just for the sake of, say, if this was ever an final exam problem, just like we mentioned on the prior problem, if this is all absolutely correct on paper before it goes into the calculator, not the prior step, you said what f at x naught is, cosine 0. If all this is down here, I'll give full credit to that. So that way, if you did make a simple calculator mistake, for example, if you were in degree mode, but you should be in radian mode, always for calculus, unless the unit is specified as degrees, we could potentially get a weird number, but you would get full credit for showing this. That way, we're not going to emphasize credit for using the calculator as much. It's going to be more about the calculus itself. But we should still approximate it to see if we're in the right ballpark. For example, if I got a negative number, something went completely wrong, so we might spot an error this way. So pi divided by 8 times cosine 0 is a 1, so we can go pretty fast on some of these. Not that one. It's cosine pi over 8. You can calculate that using addition formulas and all that stuff, but you don't have to. We're just approximating these anyways. Plus cosine pi over 4. That might be faster to write than root 2 over 2. I don't know. Maybe that's not true. Let's just put it that way anyways. Plus cosine 3 pi over 8. And when we have all those in there, this tells us the area comes out to, I'll go with 4 significant digits again, 1.183. So the area is 1.183. Like we mentioned before, this is an overestimate because all of our rectangles overshot the area. So this is an overestimate. At this stage, our work is complete. And again, this is pretty similar to how the problems are going to look in the actual homework set as well. The homework set is going to ask you to come up with that number and say whether it's an overestimate or underestimate. But a good amount of the work is to visualize the problem too. So this part is also required in the homework, sketching the curve and the approximating rectangles. We'll do it again with a different kind of rule, the midpoint rule. But any questions at all, folks? Finalizing this one? Okay, so far we're getting a good handle on how to calculate these areas. Not the most efficient way possible. We're just leading into how is the fundamental theorem of calculus going to work to help us solve this problem in a reasonable amount of time. This is tedious with even just 4 terms, but we're working our way up to that. If you're curious, it turns out that the area is exactly 1, which is kind of remarkable when you think about that. Area under this curve in green from 0 to pi over 2 for a really complicated function, and that's an irrational number, pi over 2. Area is a perfect 1 for this. We'll be able to see exactly why once we take a look into fundamental theorem of calculus. But for the moment, let's take a look into the next kind of problem along these lines. When we're looking into, say, the left endpoint rule, the right endpoint rule, if the function is always increasing or always decreasing, these rules tend to be biased. And we mentioned if you want a better approximation, you could do this whole problem over again with the right endpoint rule, 4 subintervals, average the answers. That happens to be called the trapezoid rule, studied in Calculus 2. Or do something entirely different. You could use, say, the midpoint rule, which is going to balance the overestimates and underestimates, and give you an actually pretty remarkably accurate answer for a small amount of intervals. We're going to use 4 approximating rectangles once again on this one. Function is 1 over 1 plus x squared. This function is always positive, and we're going to go from -2 to +1. So same kind of problem. This time we're using midpoints, so we'll show how that goes. But we'll set it up about the same way. Let's set the stage for the axes, going from -2 to +1. This time I just want to write down the horizontal axis, just that. Then I know -2 is going to start here. But before I put down too many points, I don't want to put -1, 0, 1. Sure, that's going to go from the left endpoint to the right endpoint, but it's not going to match the fact that we're using 4 approximating rectangles very well. We want to put our tick marks in a way that matches this midpoint rule. So the very first thing we should really do before we build out our whole entire axis, and even put down a vertical axis, which would say where the 0 tick mark is, we should calculate the delta x part of the problem. It's always the same formula, b minus a, divide by n. When it says 4 approximate rectangles, it's implying n is 4, just like before. So 4 goes down below. The value for b and a are, b is the upper bound, a is the lower bound. So we're going to go from 1 minus a -2. That comes out as a 3/4. I think for this problem, it's slightly more convenient to write it in as a decimal, 0.75. Unlike, say, pi over 8, we have an exact value here in decimal form. So that's going to be the width of all the approximate rectangles. And when we go to get our next tick marks, that's all we're doing is we're adding on the 0.75. So the next value, let's maybe write them over here first, just to match the way we did it before. We had a equals x naught, which is going to be -2. The next one, we take that -2 value, add the delta x. So this is going to become -1.75. Excuse me, let me try again, 25 rather. So just add delta x to get all the next values. X2 is going to be -0.5. X3 is going to be 0.25. We add 0.75 delta x to x3, 0.25, we get exactly 1. We can check our arithmetic. That's got to be b, and it is. That's the upper bound of 1. So if we're using 4 approximating rectangles, we do expect 5 points. And this time, we're using the midpoints. So in a certain sense, we're going to be really using all 5 because we have to find the average value between x0, x1, x2, x1, x2, x2, x3, and so on. But this gets us started. This is going to allow us to build out the horizontal axis. So let's put in the next points, -1.25. Probably want a longer horizontal axis now that I'm looking at that width I put there. -0.5. here's positive 0.25, and here's 1. So now that we know where all the actually useful points are for our purposes, let me fix this negative sign. That looks funny. Okay, now that we know where all these values are, this is a good time to put down the actual vertical axis. It's not going to be right here. It's going to be more like, say, around this spot. And there it is. Here's our x-axis, y-axis to match the problem for midpoint rule. Now we need to plot that function, but it's really not too bad. You can just use the point plotting method. At 0, this is exactly 1. So we've got a point here to plot. We plug in 1, this is exactly 1/2, so halfway down. We put a 1 here just to set the scale. That means at -1, it's about at 1/2. -1 would be right around there, symmetrically around the axis. If you plug in -2 inside the function f, let's see, -2 squared would be 4 plus 1 is 5. That'd be 1/5 for about a 0.2. So roughly about here. So that's the rough sketch of the function f of x. Here it is with the dots connected. I missed. Let me try again. Your sketch, again, it's by hand, so it's understood it doesn't have to be perfect. I think I usually mess this up pretty bad, but that's better than I usually do. I'm kind of happy with that one. So there's y equals f of x. Now we need to sketch, well, we did the graph. We need to sketch the approximating rectangles. Any questions with the process so far, getting to this stage? Okay, now here's the next part. We actually need the midpoints themselves. The midpoints, because we're averaging, we call them x bar, borrowing from statistics. The first one is x bar 1. It's the average between x naught and x1. So we could write as a formula, x naught plus x1 divide by 2. Let's go and put that in the calculator. X naught is -2 plus -1.25. Not the world's most convenient numbers. Divide by 2, -1.625. So that's our very first midpoint. Kind of tedious to calculate these all out, but you know what? There's a big shortcut here. When we're going for the second midpoint, we can reuse the formula. It's x1 plus x2 quantity divided by 2. That's always going to work out. But the distance from one midpoint that's here to the next midpoint right over here, it's still just delta x. So you can just now add delta x to get all of the other midpoints once you have just one. And that saves a fantastic amount of time. In your calculator, you can just take what you have and go plus, let me reveal delta x. Here it is, 0.75. That's the next midpoint, -0.875. Then just keep on doing that. You can go times 2, or let's just emphasize we're adding delta x by going plus 0.75 again, -0.125 for x bar 3. Here's the last midpoint, x bar 4 plus 0.75 is 0.625. And I'll just call them on the graph so the graph doesn't get too busy. X bar 1, X bar 2, X bar 3, X bar 4. We do need to have those positions placed for when we go to graph those rectangles. And checking these positions, X bar 3 should be slightly negative. That looks about right, somewhat close to 0. X bar 4 looks like it'd be close to about 0.5. It's to the right of it, and that means 0.625 looks about right. So all these numbers look like they're in about the right spot. Now we're ready to graph those rectangles. Let's use the same color that we did before, just for the sake of parallelism. Now, once we have the midpoints, it's whether it's a right endpoint or left endpoint or a midpoint like in this problem, the points we select determine the height of the approximating rectangle. So if we have a midpoint there, we go up vertically until we hit the curve, and that's the height. The width will go from -2 to -1.25. So that's why we really need these numbers on the graph as well, not just the midpoints. So once you have the height, go from the left to the right across those numbers. Let me see if I can draw that just a little bit better. In our very first approximated rectangle, it's hand drawn, so it's not perfect. It looked like it kind of melted on the right, but let's let that stand to say we're not expecting you to be a perfect artist or use a ruler every time. But notice that over here to the left, it's overestimating the area. The rectangle's above the actual curve. To the right, the rectangle is below the curve, so it's underestimating the area. And that's the nice feature about the midpoint rule. If your curve increases, decreases, has lots going on, the midpoint rule gives us a balance between overestimation, underestimation. So it tends to be pretty accurate for the amount of intervals we use. For the next part of the sketch, go where x bar 2 is. It determines a height here. A rectangle has to go from -1.25 to -0.5, exactly at that height. And then rinse and repeat. Let's do kind of a lazy shading on him like before. X bar 3 is about up there. The rectangle goes up through that point, stopping at 0.25 for the width. And here's approximated area here. Finally, X bar 4, shorter rectangle, goes from here to here. So that's the visualization of the problem. It's tedious to draw, but it's important because if we're showing how the process of any one of these rules, particularly the midpoint rule, is actually approximating area for us, this is the mental picture of what's going on in the background. So at this stage, we can put everything together and get that approximated area. Any questions or comments to this stage? Okay, well, let's write this out. First, just like we did in the last problems, I'll put down the formula for the midpoint rule, and then we'll just evaluate it. So area will be approximately equal to, and this is a decent approximation, M4. M4 by formula is delta x multiplied by the group, switch colors, f at x bar 1 plus f at x bar 2 plus f at x bar 3 plus f at x bar 4. So there it is as a formula. We have to go beyond this to get full credit on a homework or an exam situation. If you're extremely confident in the calculator and you can just type it in and no worries that you made a mistake, you can just give me that number. But for the sake of partial credit, here's where the insurance is. If any mistakes ever occur in the calculator, this next line is full credit, like we mentioned on the other problems. Put down the actual value for delta x, 0.75. And then show all the function evaluations. If it says f at x bar 1, we take that x bar 1, -1.625, and plug it into that original function at the top, f of x. It's a bit tedious, so let's copy these out down. This is going to be 1 over 1 plus negative. This is going to be squared, so it will come out as positive. That's a good shorthand. I think that's confusing on the notes, so I'll put in the negative 1.625 squared. Again, if you lost the negative sign, that would simplify down because of the power 2. But putting it in verbatim, that's term 1. Now we go to the next term, look up the x bar 2, look up the f of x function, add 1 over 1 plus negative 0.875 squared, and rinse and repeat. For this one, it's going to be plus 1 over 1 plus negative 0.125 squared. And we're on to our last one. At x bar 4, it's 1 over 1 plus 0.625 squared. We can close the group here and now get a number out. We'll approximate this one as well. So if this again is all correct on paper, then even if you made a simple mistake on the calculator, and I can't tell you how you got your number, you still get full credit. Well, we're ready for the calculator, but any questions doing the evaluation to this step? Okay, so here's what it's going to look like in a calculator, just typed out, all just like that. It's sort of tedious in a calculator, but I'll type it out just like we see here without using any tricks, just so that we see what it would look like on a real calculator. So 0.75, 1 over 1 plus, and the calculator, I will take the shortcut that you don't have to put in the negative if you're raising this to power 2. Just a lot easier to type it all in. 1.1625 squared. Squared, there it is. Then go plus 1 over 1 plus 0.875 squared. Now we're on to the third term, plus 1 over 1 plus 0.125 squared, plus 1 over 1 plus 0.625 squared. And finally, that's our answer. To 4 significant digits, this is a 1.909 upon rounding to that digit. So the approximate area is about that. And this one is actually pretty close. This is decent for just using 4 subintervals. So we did it, folks. That's another decent area approximation. Any questions or comments getting through this stage here? Okay, this one didn't ask us to determine if it's an overestimate or underestimate, because with the midpoint rule, not really a fair question. That's really hard to determine just by visual inspection. Caleb says, what's the difference in using the midpoints versus the other way? Well, if we used, say, the left endpoint rule, right endpoint rule, this one would have been a little bit more biased. Say we used the left endpoint rule, where the function's increasing, we would have gotten a pretty big overestimate, slight underestimate right here. And so this one, the midpoint rule, just balances the overestimates versus the underestimates a lot. Say if we look into this last one we did here, we did the right endpoint rule, it would have been biased in the other way, it would have been an underestimate. This one is clearly a pretty big overestimate that we see here, but the midpoint rule balances it out. It gets much, much closer with the same number of subintervals. I'd say, yeah, it's absolutely better for estimates in just about every situation. To find a situation where midpoint rule is worse, but something else is better, you'd have to design a particular function that is tailored purpose to show midpoint rule could be worse. So it's not true for every exact function, but if you grab a random function, more likely than not, midpoint rule is going to work out better. There's kind of a trade-off though, right? Here, it was really easy to get the points, do the computation. The midpoint rule, you had to get the points, get all the midpoints, and then it was a little bit bigger of a computation. Would have gone a lot faster if I could have just used those. So there's a speed trade-off in the midpoint rule, particularly if you're doing this by hand instead of writing a computer program to do it. Other questions at the moment? Okay, maybe another thought about this is, what can we do to make the estimate even better? Still using the midpoint rule, for example, you could change n from 4 to 4,000. Now we're not doing that by hand. That could take a very long time. Some people could probably crank that out if that's just fun for them. You might start writing a computer program, a loop that just does this all for us so that we can automate it. But even at n equals 4,000, it's still an approximation. Now you have to do work to say how accurate is that approximation to the true exact area. Another thought is you could use calculus. You could do the following and say the area, let's put a little border here to say this is an additional thought to go along with the problem. We can say instead the area is dead on exact to the limit as n goes to infinity of this summation. Let's take delta x times the summation first. I'll put it to the left. You could put it either to the left or the right. It'll be f at x bar 1 plus f at x bar 2 plus this is going to be particularly possibly a very large number for n, right? If it's going to infinity. So we use this shorthand. Instead of writing out what could be 10 to the power 30 terms, we'll just say, and so on, up to f at x bar n. Delta x is still b minus a divided by n. That's kind of curious because if n is going to infinity, the width of delta x is going to 0. The graph above, the width of all these rectangles is going to 0 itself in the limit. So this says more and more terms, smaller and smaller width. If the area can be calculated this way, as the limit as n goes to infinity, we will define that to be the notion for the exact area under this curve. So this is how limits get involved. And pretty much it's the segue to the last formulas before we go into the next notes. Only trouble with writing this down is that it's tedious to write f at x bar 1 plus f at x bar 2 and so on. But there's a big shorthand for that. The shorthand would be this. That whole thing could be rewritten as summation I goes from 1 to n f at x bar I. That's just our shorthand for repeated addition of when I is 1, it's x bar 1. When I is 2, it's f at x bar 2. It's the second term. When I is 3, f at x bar 3. It ends at n. So when I updates to n, it's f at x bar n, and you get the last term. So that's our shorthand for repeat addition of these kind of terms. And that's just all that's being defined here. So-called sigma notation is just our way to define repeat addition. You might have seen it in other math classes, but we're just defining it here as a refresher. So think of this whenever you see it as just shorthand of adding a1 plus a2 plus a3. The index, which is I, starts at a 1 because the term starts at a1, updates to the next integer, 2. You plug 2 in there, and summation here just means add a2. Index updates to 3. It's kind of like a for loop in programming. Add a3, add an minus 1, but then you reach the upper bound of that index, n. This becomes an, and then you just add it on. Same idea as what we're seeing up here. So our formulas are going to compact in just a little way using summation notation. Or sigma notation is a better way to describe that. This is the Greek letter sigma. Any questions at all, folks, with sigma notation or so-called summation notation? Okay. Well, I don't have a last problem, but this is more kind of just a reiteration of what we're saying here about this limit. If we have a curve, say like this one that's in blue, the area of that region S under this curve in blue, if the graph is a continuous function f, will be the limit of the sums of the areas of the approximating rectangles. F at x1 delta x, this is the right endpoint rule, so we call it Rn. But we want to take the limit as n goes to infinity, and this is what it would look like. In summation notation, that's just a compact way to write that. So the area could be defined in this way. Here's the interesting thing about the left endpoint rule, the right endpoint rule, and really any other rule whatsoever. If this limit actually exists, it gives you the same exact area if you took the left endpoint rule. If you put a limit out in front, you're getting the exact area either way. Left endpoint rule, right endpoint rule, it's all going to be the same. If it's the right endpoint rule, you start at f at x1. If it's the left endpoint rule, you start at f at x naught, just like we did in the notes. And this generalizes even further. It says, instead of using left endpoints or right endpoints, or even midpoints we could have added to the sentence, we can take the ith rectangle to be the value of any number xi star. That will just be referred to as just some random sample point. Maybe a formula generates it. Maybe the sample points are midpoints. But it could be anything that's between an interval, xi minus 1, up to xi. Your xi star can be any point whatsoever in the ith subinterval. Then you could just rewrite it as f at x1 star. A random sample point right here, determine the height of this rectangle, times delta x, that's the width. Repeat at f at x2 star, a different sample point. That one looks like a midpoint. Determines the height, multiply by the width. If you keep on doing that, you end at a finite term. That's not the area, that's the approximation. But if we say keep adding more and more terms, take the limit as n goes to infinity, you get this structure. Limit of the summation, I goes from 1 to n, of the height, f at xi star, and that's the height going this way, times the width, delta x. So if you take the limit as you go up to infinity, that's the dead-on exact area. So as far as computing exact areas goes, if we're not approximating, these rules are considered equivalent in a certain sense. Well, any questions at all with just the concepts being mentioned here about getting the exact area? Okay, well, that's the conclusion to section 5.1. Like we mentioned at the bottom of the notes here, that's a lot of formulas, but you don't have to write these down and try to memorize them. The way we're going to be using the right endpoint rule, left endpoint rule, and the midpoint rule is the way we did above in the notes. But these are the things we're going to study in the very next section when we go to define the so-called definite integral in section 5.2. So now that we're involving limits, we're really into calculus. That's where all the interesting things come from, some form of a limit. That's how we've defined differentiability, continuity. And now when we go to the integral, this is how we're going to define integrability. That's kind of a big word. Revision is just something small in the notes. I had the numbering of some problems wrong, so I fixed it there, so nothing major. So example one of these notes is kind of just a refresher of the role of limits. And the definition below is going to be essentially tying in what we saw in the very last section notes, how it ended. And we'll define before we're very far the definite integral of a function f from a to b. So think of this as kind of a slow start, just tying up together a bunch of concepts that we've looked into since week 1 of the course. There's 3 big concepts in calculus. I mean, we mentioned this on day 1, but we didn't know what continuity and differentiability, integrability were. Now we do, so this problem becomes much more meaningful. All 3 of the concepts are all defined through a limit of some form. So understanding the limits is a major objective on the class. And I think I gave a hint that these kinds of things could be on exam 1. It didn't make it on exam 1, so even a bigger hint, it means you can expect something about this one and this one on the final exam. So part A says, we want to express this information in the form of a limit. And this one is the information that f is continuous at x equals 3. The way we write this down as a limit is continuity at 3. Continuity is defined through a limit, so we write limit. If it's continuous at 3, we mean as x tends towards 3. For involving a function f, we have to write in an f of x there. But then the conclusion to this whole problem is nothing but direct substitution. Continuity means when you go to evaluate the limit, all you're really doing is taking f at 3 and nothing more. So that's how we defined continuity. We did a lot of other things through graphs to get an intuitive feel for what does this really mean in practice when we look at the graph of a function. But at its heart, it's nothing but that. So that's continuity. We're going to look into differentiability. F prime at 3 is 9. And then the next definition will be integrability. But any questions first before we go to part B? Okay, so for part B, one formula I'd probably think about before trying to write down this equation in the form of a limit is, let's just write down the definition of the derivative. The derivative definition goes, the derivative of f at any value x is the limit as, let me fix that, not an x, it's the limit as h goes to 0, f at x plus h minus f of x divide by h. And the way we came up with that equation, we developed it ourselves on the notes, is we just found out how to take the slope of a secant line. Then we said if we take the limit as it goes to 0, the secant line becomes a tangent line, and that came just from the slope formula itself. So if we're saying f prime at 3 is 9, this is essentially all that's going to happen. F prime is going to be a limit as h goes to 0. So that's how the derivative is defined through the limit itself. It's going to be the limit involving this number here, 3. Let's write this as f at, in place of where the x is, put in a 3. 3 plus h minus f at 3, all divide by h. We said the derivative equals 9, so we have to also capture that there's an equation here. This equals 9. So the equation for the derivative in the form of a limit means that this limit as h goes to 0 just lands at the number 9. So those are two limit equations so far for continuity, differentiability. Here, we're going to revisit the definition on just the last page of notes, 5.1, and define integrability next. So this is already pretty much chapter 2 in its entirety with these two limits right here. Now we did a lot of work on differentiation, and we're turning over to the definite integral from a to b. So this is our next concept to look at. Any questions with that last part B before we take a look into the next one? Okay, so here's our new definition. The purpose of this is to define the integral, the thing we see down below. So let's put in some good work using all this white space we have here to show how these concepts connect as a visual for our brain to digest. We have a function f defined from a to b. So let's start there. Same as the function that we have right here and right here in the definition below. This time when we go to use the graph, let's emphasize both quadrants 1 and 4. I'll let a go from here. Let's add some values. This is a equals x naught. This will be x1, x2, x3, and just a little bit further, let's let that be the value b, which is x4. So there's our graph. Let me extend it a little bit below, a little bit above as well. Let's just do a whole new axis on that. Let me see if I can fix that. It's a little bit better. Okay, let's graph the function f now. Starts at A. I don't want it to be weird in any kind of way, so it's going to be graphed in a nice continuous way. At B, though, one thing that you might have found kind of curious on all the problems we looked into in section 5.1 was that the functions were purely positive functions. They never dipped below the x-axis. They never even, well, they did have an x-intercept, but they never became negative at any point. Let's let that happen this time. Here's the function, and it does that. We still want to find the area under the curve, but what we mean by area is a little bit different. It's going to be considered a signed area or a net area. This area will be positive. This area will be negative. We'll add them together. And it looks like the net area for this graph would be negative altogether. So we have a function going from A to B defined on the interval, closed interval from A to B. It's divided into n subintervals of width. Delta x is b minus a divided by n. So that's the width going from A to x1, x1 to x2, and so on. All these have the same exact widths. X naught through xn are going to be the endpoints of the subintervals as we have drawn down below. And using the notation from the last image in section 5.1, we can pick any sample points whatsoever when we determine the heights of those rectangles. So let's come up with let's just go with green. These are going to be the sample points that are in the ith subinterval from xi minus 1 to xi. They can be anything whatsoever. They could be a left endpoint. They could be the right endpoint, a midpoint, or just some random point. Let's let it be a little bit random. This would be x1 star. The sample point determines the height of the rectangle. The height goes here. And that's the first approximating rectangle. This would be a height, f at x1 star. And because f at x1 star is above the x-axis rather, it's a positive value, we think of this as positive area. But it doesn't always have to be positive area. If our next sample point is x2 itself, that's allowed. Let's use a little arrow here. x2 star is the right endpoint, x2, then the height of the next rectangle is down there. That means the next approximating rectangle, let me try a little harder on that one, will look about like that. And that area is now negative because we're just going to take delta x, the width, times f at x2 star, but that's now a negative value. It's on the negative end of the y-axis. So when we go to use the same process from the very last lecture, we can now extend to positive areas and negative areas. Let's throw down the last two sample points just to end this. Last one looks like it's at a midpoint. x3 star, we'll just call it still a sample point. It could be slightly off to the left, for example. Gives us a value right here. That's going to be another negative region. And the final one, let's just put something random here, x4 star, gives us that value. And that's the final approximating rectangle. So the signed area would be approximately equal to, take the delta x, the width of all these rectangles going from A to x1, x1 to x2, and so on, multiplied by the group, f at x1 star plus f at x2 star plus f at x3 star, and if this ever happens to you, just drop a line and keep on going, plus f at x4 star, and that's our signed area. That area is probably a pretty crude approximation, sometimes underestimating, sometimes overestimating, either a positive or negative area. But we can say the exact signed area under the curve y equals f of x is when we put a limit on it. So if we take the limit as n goes on to infinity, we have the exact area. So this is what the picture looks like for integrating, approximating an integral where n is equal to, we had 4 approximating rectangles. But now imagine this is really actually meant to be very, very dynamic. I just can't draw an animation. Imagine n updates to 5, 6, 7, moves through 100, 200. All of these rectangles get narrower. No matter where the sample point is, you can see that the rectangles are going to just look like some kind of solid shading under the curve in blue. That means we're taking the limit as n goes off to infinity, and the whole shorthand for this entire thing, which is referred to as the limit of Riemann sums, is called the integral. So if the limit exists, that limit, we'll say the function f is integrable on the closed interval from a to b. So that's the whole definition of an integral itself, and what it means to integrate. Notice the word definite. This will be important later because we have the idea of an indefinite integral in section 5.4 that we'll take a look at. But so far, this is what the picture looks like and what the limit looks like when we're integrating. So there's a lot of new notation that goes along with this, but any questions or comments at the moment, putting these ideas together? Okay, now one downside to these limits are they are very, very hard to compute. In the reading in section 5.2, the author shows us how to do 1 or 2, but I decided not to assign that as a homework question because right away in section 5.3, we're going to see the fast way to do that limit through the fundamental theorem of calculus. The reason we're introducing this limit here is to show what that really means. When you see this on paper, it's going to start to feel kind of abstract. But if you have your mental image that it's really this, you're taking these kinds of pictures and you're making a dynamic movie where the number of rectangles just gets higher and higher and higher. Every integral sign is a limit of Riemann sums, in other words. You'll have a good idea of what's really happening in the background every single time we write down a definite integral like this one. It's a hugely dynamic geometric object trying to find that area by taking a limit. And there's lots going on. There's lots of decorations. There's a weird symbol here. This is thought of as being an elongated S, which comes from the sigma notation there, which reminds us we're taking repeated sums of outputs for the function. So think of that integral sign as elongated S, meaning to sum up. And here's all the notation that goes along with these concepts. And a nice theorem down below. So there's a lot of moving parts. We call the symbol here the integral sign, whether it's a definite integral or an indefinite integral. We'll see in 5.4, we'll still call it an integral sign. A is the lower limit of integration. B is the upper limit of integration. So we go from A to B. F of x we refer to as the integrand. So integral sign from A to B, f of x, and dx is a reminder that we're integrating with respect to x. Turns out that's absolutely important as well. Hang on, struggling with my pens. Let me fix that. Integrating with respect to x as a variable. To the right-hand side, that's just our definition for what the integral really is as a limit, just like defining continuity and differentiability. The whole thing here is a limit of Riemann sums. That part, the summation, is the Riemann sum. Throw a limit in front of it, and it's the limit of Riemann sums, named after Bernard Riemann, German mathematician who studied these kinds of things. And maybe one more bit of verbiage here. When you see that, the way people typically read this out from left to right, bottom up, is the integral of f from a to b. That's how that whole symbol would be read as. So the integral sign along with the dx is considered to be one whole symbol, much like dy dx is one whole symbol to say derivative of y. So these limits, they're complicated, but there's one gigantic theorem that's really helpful for our purposes. Knowing when the limit exists or not boils down to continuity. If your function is continuous on a closed interval, then the extreme value theorem says it'll have an absolute minimum, absolute maximum. So there is absolutely going to be an area to that if you can find a minimum and a maximum, absolute. But also says if it's continuous on the closed interval from A to B, or only has a finite number of jump discontinuities, not an infinite number, then f is integrable on A to B. The integral is guaranteed to exist, which means that limit exists, and that's how we define the signed area in the very first place, putting a limit in front of that entire term. So continuity comes back and it gives us a condition right away for when you can integrate a function, get an answer out, and the answer to this would be the signed area. So that's a lot of talking so far, but there's a lot of notation and ideas that goes together with integration, even more so than differentiation. Any questions or comments as we defined all these moving parts and components? Okay, our next example that we're going to take a look into, really our first example on these notes, is seeing how to transfer from the limit to the integral, or vice versa, from the integral to the limit. It's really a similar kind of problem that we did in example 1. That's why we refreshed this example here. We're trying to see how to take continuity as a limit, differentiability as a limit. And so that's the theme for the very next question. What we did here to help us with these kinds of formulas is we're looking into specifically the right endpoint rule for theorem number 4. The thing that's nice about the right endpoint rule is the area is going to be exactly the same if it's the left endpoint rule, the midpoint rule, if you're taking the limit as n goes to infinity. And the right endpoint rule is probably the most straightforward one to write down. This is the formula for the right endpoint rule right here. When we're using a definite integral, we're finding the exact area under the curve f of x from a to b, which means it's a limit of the Riemann sum. And if we're doing Rn, that means we just put xi here. Xi is defined in this way, a plus I delta x, where a comes from the lower limit of integration, b is the upper limit of integration, and delta x, just like everywhere else in the notes, is defined in this way. I here is not the complex number, it's just the indexing for our sum that we're taking a look into. So we're going to do two kinds of problems, just practicing with this concept here of going from a definite integral and making it concrete what we actually mean, writing in terms of a limit. These kind of examples, both 2 and 3, this is where the revision is for the notes, I had the numbering wrong here, are very common on final exams. I wouldn't ask both though, just one or the other. So we're going to take this limit, express the limit as n goes off to infinity of summation I goes from 1 to I, xi times natural log xi cubed minus 1 delta x, a very, very complicated limit, in the form of an integral on the closed interval from 1 to 7. It has a bunch of follow-up questions. What is the lower and upper limit of integration? What is the integrand? So let's address those first, and then we'll convert over the limit. So when it asks for the lower and upper limit of integration, it's just referring to those numbers, 1, 7. Let's write down a little bit more specifically. Lower limit. I'll abbreviate it as lower limit to mean lower limit of integration equals always the value a, which in our problem is 1, coming out of that closed interval here. Upper limit is b, which is going to be 7. So that's the lower and upper limit of integration. Notice it always goes from lower to upper once we determine what lower and upper are. The integrand, kind of like saying radicand. Radicand is the thing under the square root or cube root. The integrand comes from this. So, in other words, it comes from whatever the function is, but we don't write down that as the integrand. That's not exactly the integrand. It just comes from that. When we go from the limit and rewrite it as an integral, notice what happens to the variables. If the Riemann sum is f at xi, it's actually the integrand here as a f of x. We just change from xi to x, and that's all we have to do. So the integrand is f of x, which is equal to, go into the Riemann sum for xi, wherever you see them, just swap x, and you've got the right integrand. So it will go x natural log x cubed minus 1. So that's the integrand altogether. There's still one more object, that delta x, but delta x, when we're looking left and right, it just turns into dx. Dx is here is just a symbol, whereas over here it was the geometric object, the width of the approximating rectangle. So those are the 3 moving parts, lower, upper limit, the integrand, and now we can say, putting this all together, put a fancy therefore, the limit as n goes to infinity of xi, natural log xi cubed minus 1. Hang on, I forgot one big thing there. I need a summation. Let me see if I can squeeze it in front. Summation as I goes from 1 to n. It's not a Riemann sum unless we're saying add up a bunch of things. So there's the summation symbol. Now it's a limit of Riemann sums. We threw in the limit. But all I'm attempting to do is just copy that part down right there. It's worth copying because the process is, in this formula here, going from the limit of the Riemann sums, all you do is put down an integral sign, we drop the limit and say integrate from a lower limit a, which is 1, to an upper limit b, which is 7. We put in the integrand f of x, and in this problem, it's x natural log x cubed minus 1 dx. And I did forget one thing. There's a lot of moving parts here, it seems. Delta x, that part here became the dx. I feel like I'm running out of color, so we already used the yellow one, so let's use a different color. Orange usually means I'm running out of colors to describe the problem. But that's the whole process. It's kind of nice in a way to go this direction to convert into a definite integral. You just take your closed domain, go from 1 to 7, drop i's, and just copy x natural log x cubed minus 1. And delta x just turns into a symbol to say we're integrating with respect to x. We put a dx on the very end. So that's the process going from right to left, limit of a Riemann sum, into the definite integral. Now we want to reverse it, go from the definite integral into the limit. But any questions on doing it in this direction? Okay, and like with any conversion, if we can convert in one direction, we must be able to convert in the other direction. Purpose of doing that is just to study exactly what's going on with both the integral and the limit of Riemann sums to connect the concepts together. So let's try this out again on example 3. Here's the formula we used on example number 2. That should be about right. Let's get this started. So this time we have a definite integral. This is the area under the curve from of x squared times e to the power negative x as we go from 1 to 5. We want to write this in the form of a limit. This is a really strong set of instructions here. You do not have to evaluate the limit. We're just writing down the limit itself. And we'll also give a quick explanation of how we know the limit exists at the very end. So now that we're reversing the direction, probably the first thing we should do is look at the limits of integration, take a look into the integrand, x squared e to the x, and if we're going to write it in form of a limit, we should start calculating these things. This is the trickier direction. Step 1 is calculate delta x. So delta x is b minus a over n. But what's new this time is we don't have a value for n because when we go to write it as a limit, n is changing, n is going off to infinity. So we can't put a definite number there. Nonetheless, the a and the b come from the lower upper limit of integration. So this is just 5 minus 1 divided by n, which means this becomes a 4 over n. So we've got delta x. I would consider that to be a strong step 1. And step 2, if you're going to write this in the form of a limit, you really have options. You could use the left endpoint rule, the midpoint rule, a fancier rule. There's a trapezoid rule, Simpson's rule, studying in Calculus 2, and the methods just keep on going. Or the right endpoint rule in theorem number 4 is just the most convenient one to use if we're writing something as a limit. So what I advise is use this theorem, and the next step is say what xi is. So xi is going to be a, following the formula down below. A in our problem is the lower limit of integration, so it's going to go 1 plus I times delta x, whatever delta x happened to be. So here's our 1, and that means xi is just going to be 1 plus, well, other substitution is delta x is 4 over n, so this would become 4i over n. Let's use that same color coding for delta x. So we make that substitution there. And that's a strong step 2. Once we have that, takes us to the step 3. We know what the integrand f of x is. F of x in our problem is x squared e to the power negative x. F of x is x squared e power negative x. But when we go to write this out, when we're writing this out in the form of a limit, the instructions imply we'll say what that really is in our context. So we next calculate f at xi using the formula for f of x and the formula for xi itself. Essentially, we're just taking xi, putting it in place of x everywhere it occurs. So this will be 1 plus 4i over n squared e to the power of negative 1 plus 4i over n. So we took xi and just put it in place of x for f of x. So there's the f at xi. And the final, fourth and last step is we can finally write down the answer. We're integrating from 1 to 5 of x squared e negative x dx. So those are the limits of integration. Here's the integrand, x squared dx. Dx here is just a symbol to say what we're integrating with respect to as a variable. It's x. And we want this in the form of a limit, so we're pretty much there. It's a lot of preliminary analysis first. We have to find out what are all the moving parts down below to get that limit. But the next steps are just put it together. Limit, n goes to infinity. of the summation, the Riemann sum from I goes to 1 to n of, next part is f at xi. We're just copying that in. So 1 plus 4i over n, e to the power of negative 1 plus 4i over n. And the last step to not forget is dx here as a symbol becomes a delta x to the right, where it's now the width of the approximating rectangles, same ones that we were doing in section 5.1. So that's what the limit is. When this says to integrate from 1 to 5 x squared e to the power negative x, what it's really saying to do is evaluate that limit. Kind of a crazy concept putting it all together, but this is where the fundamental theorem of calculus is going to help us. We wouldn't attempt to do this limit right here by hand. This one might require an extreme amount of ingenuity to get through. L'Hopital's rule, for example, isn't going to help, but we do know this limit exists. The theorem over here told us if f is continuous on a closed interval, then f is integrable, which is another way to say the integral exists, which is just another way to say the limit exists. So we started with the continuous function. This is continuous on the entire real number line. So that means we can now say the limit exists because f of x, which is x squared e to the power negative x, is continuous on 1, 7, the closed interval for which the whole function was defined on. So there is absolutely an area on this that we can compute, but we just need to find out ways to actually make this integral happen. It can be done. It can be done by hand, and we're going to do it without actually doing the limit itself. Well, those are two kind of tough conversions. Any questions on getting through either one? Okay, well, we're towards the last part of the notes. For the last part of the notes, we're going to take a look into a case where an integral does not exist. I think that'll be a good one to start off fresh when we come back on our Thursday's class tomorrow. And then we'll look into properties of the definite integral. And even though this looks like a long list of properties, there's a kind of a nice thing about this. Integration is defined in terms of a limit. We were just converting from an integral sign into a limit and vice versa. But because it's a limit, all of the limit laws absolutely do apply. And for example, if we look at, say, this limit law, this definite integral property right here, property number 4, says if you're integrating a f of x plus g of x, you can actually break down whether you're adding or subtracting into integral of the function f plus or minus the integral of the function g. The reason that works is just property 1 for the limit laws. This is just a limit here, this is another limit, and you can just place them together. Another interesting property is that the integral of a constant multiplying a function is just a constant multiplying the integral of a function. In fact, that works for differentiation as well. This idea works for differentiation. It was called the sum rule. The derivative of a constant times a function is the constant times the derivative of the function. And it's the same property for integration. Why does that work? It's because of, where is it? Property number 3. The integral right here is just a limit. So you're taking a limit of a constant times a function. You can take out the constant, take the limit of the function, and that's the heart of what's going on with this property here. So lots of other properties we'll take a look into when we come back next class. But that's just the tie-in. One of the reasons we emphasize the limit so much is once we know something is a limit, everything we've done involving limits now can be leveraged into the problem. And that's where a majority of these properties are actually even coming from. And same for differentiation. So we'll come back on our Thursday's class, look into properties of derivatives, refresh, and look at why the integral here does not exist, even though it looks like a harmless one. And then we'll be soon in section 5.3, Fundamental Theorem of Calculus. Bill, any last questions or comments at all, folks, before we call it a night? Okay, and again, kind of a preview to what we're getting into with the fundamental theorem of calculus is it's going to give us an alternate way to find this signed area, which is what that definite integral really represents, without having to do the limit. And we hinted at this at the very start of the section 5.1 notes. The way to do this right here, which is effectively the same way to do the limit, is you have to find an antiderivative to that function. We must ask and answer, what did we have to differentiate to get an x squared times e power negative x? So that's where calculus is going for the last part of our course, and that's where calculus 2 is going, how to get the antiderivative so that you can integrate and not have to do the world's most miserable limit either. These are fantastically complicated. Every new function requires some new ad hoc method to do the limit if you did it directly. But this is where we'll end class today. We'll come back to it a little bit more fresh and do some more computations, less theoretical defining stuff like we did today. Have a great night, folks. I'll see you all tomorrow.